So hope Mark is there and ready for. I think we are running a bit fast, so that I would give more time to my guest speakers to talk more. And crop loss is going to be a wonderful topic. To many people are waiting for that deliberation to hear. And let me introduce again Dr. Mark, who is a co-founder and a chief scientist of WIDIS remote sensing, which is operational right now at Karnataka for different applications. And Mark is done his PhD in MIT, Massachusetts Institute of Technology, USA in 2018. And later, recently he has joined in the response of Director of Engineering Design and Senior Lecturer in University of Auckland in New Zealand. And we have been interacting with Mark since he was at MIT student, and we could see the potential research what he has done. And he has been developing a number of sensors, low-cost sensor, and on fixed wing platform to fly and go for crop mapping, particularly for retrieval of parameters for the crop loss assessment. So that's what the kind of expertise he has developed in MIT. And later, Dr. Mark was working as an engineer for product development with BMW for the international design and consultancy IDEO. And later he was working at Nepal and Ethiopia doing the product development for small scale farming. And also he is very good at teaching and has a good experience in undergraduate engineering as an instructor at the Franklin Olin College of Engineering. And Mark have been interacting with iShare and many Indian partners to see if some of the questions raised in the crop loss assessment and the crop insurance can be addressed by Mark. And so with these words, I would like to invite Mark to talk on drone remote sensing for crop loss assessment. I know, Mark, it is too early, and I'm really special thankful to you. Totally whole night you were active, you didn't sleep, and starting from inaugural session till now, and that shows how keen you are for this program and interact with us and developing friendship. Thank you, Mark, and it's you now.
Thank you very much, Dr. Sahu. Let's see. Is my screen visible now?
Yeah.
Great. Thank you. Hello, everyone. Thank you, Ravi, for that introduction. I will be talking about drone remote sensing for crop loss assessment here, and I added the parentheses around drone, and you'll see why as the presentation moves forward. Sorry, I need to make one adjustment here. That is... Okay. So it will take me a little while to get to the actual technical portion of the presentation, but the background story here is important. I'll start out talking about crop insurance in general, and really the purpose of crop insurance in managing risks for farmers. And that really leads to the motivation for this work, where it wasn't initially assumed that drones or that aerial imaging would necessarily take a part in the solution. Then we'll talk about the user needs that really led to the drone work and the remote sensing work on this project. And then so we'll get into the technical details on image registration and really maximizing the use of reflectance data from the aerial imagery. And then I'll talk a little bit about how we're moving this forward to actually implement it in the real world. So this is ICAR, this is IARI. You understand the issues that farmers face and the risks that they take every year. from pests and diseases to floods and droughts. And so I ask you, what is really the purpose of crop insurance? And the point there is really to help farmers manage risk. Now, many of you are probably familiar with the PMFBY program, the Prime Minister's Crop Insurance Scheme. But I'd like you to stop and think for a second and imagine that you're a farmer. You have a new season coming up. You take out a loan to buy seeds and fertilizer. Because you took out a loan, you're required to purchase insurance. You pay 2% of your loan amount in the insurance premium, and the government pays the rest of that insurance premium. At the end of the season, your yield is low, and you're wondering, are you going to get a payout? So what actually determines that? In the PMFBY scheme, they have a very defined process to determine whether or not you're going to get a payout based on, not on your yield, but on the yield in your village. So this map actually shows about 1,200 plots, which could be a typical village. Within that village, there are 4 samples that are taken by state officers. Those 4 samples are turned into a sample mean. And if that sample mean is less than a certain threshold, then every farmer in that village who has insurance receives a payout under the PMFBY. Now, ideally, they're searching for the real mean or the true mean in that area. But because of the cost of actually finding out what the true mean is, they've reduced that to only taking the sample mean based on 4 samples. So let's look at it a little bit more statistically. If we reorder those fields and make some assumptions, we've seen anecdotal evidence that a 10x difference in yield from what there are villages where you see a 10x difference in yield from one plot to another within the same village. For this exercise, we're going to assume a 4x difference. So if the yield ranges from 200 of whatever unit to 800, and we evenly distribute the yields within a village between those 2 numbers, then we get a true mean of 500. From those, in this case, 100 plots, we then randomly select 4 sample plots, and we calculate a sample mean. We do that over and over again, so we bootstrap Monte Carlo simulation, and we get a roughly normal distribution, which is what you see here. The key here, though, is that the sample mean that we get in any given year could lie anywhere in this distribution, from as much as 250 below the true mean or 250 above the true mean. So whether or not an individual farmer gets a payout depends more on which fields were chosen for those 4 samples, which is random, than on what that individual farmer did. So if the threshold, even if the threshold is a bit above the true mean, whether or not a farmer gets a payout depends on where that sample mean falls within this distribution. And so I asked the question, does that really help manage the farmer's risk? And that's really what was driving this project. Can we actually create an individual insurance product for smallholder farmers? Now, the good thing about the PMFBY is that it's been implemented. It works, it functions, the mechanisms are in place. They're actively working on improvements and applying technology to make it more effective. But the functional unit is the panchayat or gram panchayat. And that means that an individual smallholder farmer, that whether or not they get an insurance payout doesn't depend on what happens on their farm. Now, as a comparison, we can think about agriculture insurance in the US. It's also government subsidized, but it's personalized. Average land holding in India is about 1.2 hectare. Average land holding in the US is over 150 times that, at 179 hectare. So the question becomes, how do we actually create this? So in the US, in that situation, if a farmer purchases insurance, at the end of the season, if he doesn't have a good yield, he can file a claim. And the insurance company will send somebody out to that farmer's field in order to assess that claim and determine whether or not there's a payout. So the question comes, how do we create this kind of individual crop insurance product for smallholder farmers in India? Naturally, it's going to require technology of some kind. For the rest of this presentation, I'd like to talk about what doesn't exist yet, that personalized insurance product. So let's look for a second at why we can't just copy the US model. If you haven't thought through how insurers operate and how they choose their terms and set their premiums, I encourage you to do so. Insurance companies in general, they get a bad reputation from the media and from the general public, but they serve a vital function in an economy by helping people and businesses manage their risks. So the question we're trying to answer is, how can crop insurance company offer an individual insurance product to smallholder farmers? This is a drastically simplified explanation, but it gets the point across. Insurance premiums need to cover three types of costs: administrative, operations, and claims. If your average customer has 179 hectare of land, then the premiums that farmer pays will more than cover the operational cost of a visit at the end of the season if they file a claim. But when you try to apply the same situation to smallholder farmers in India, the model falls apart. At the end of the season, if a farmer has a claim and the insurance company has to send a person out to the field to investigate it, the farmer has paid so little in premiums that there is then no money left over to fund claims after the cost of just sending that assessor out to the farms has been paid. So how do we replace the job of the assessor with technology? How do we get reliable, accurate information to the insurance company so that they can make policy decisions? Obviously, we're here to talk about remote sensing. So that's the direction we're going. We just heard from Dr. Sahu about field phenotyping, and we heard from Dr. Agarwal earlier about using drones and the capabilities of multispectral and hyperspectral imagery in getting the information that we need. ISRO and the Mahalanobis National Crop Forecasting Center have done a lot of work on crop ID and on yield estimation from satellites. So the reflectance interpretation of crop signals is making progress. The question really comes, how do we get that information at a plot level, at a plot by plot scale, such that we can offer a plot by plot product? Now, our options for remote sensing are pretty broad. To decide what makes the most sense, we need to look at the needs of the users. Now, we could use Landsat data or Sentinel data. We could talk about drones. We could talk about large, fancy aircraft with very heavy-duty sensors on board. We could talk about tractors or handheld sensors. But we really need to go back to the users and figure out what they're looking for. So, what about insurance companies? What do they really need to know? We have to start from the ground up to define our functional requirements. Crop ID and yield are the most important. Crop ID because insurance companies need to verify that the farmer is actually growing the crop for which they have insurance. Crop yield because the insurance company needs something on which to base their payout decisions. So the crop ID really needs to be plot by plot, early in the season, and the crop yield comes in at the end of the season, obviously. The other two pieces of information here are valuable, but they're not critical. Crop health, if the insurance company can help the farmer know when there's a problem with the crop, when the crop is under stress, then the farmer can act sooner. Acting sooner reduces loss, which improves yield for the farmer and reduces the number of claims for the insurance company. So there's good alignment of motivation there for the insurance company to both collect crop health data and to provide that data to the farmer. In the case of catastrophic loss, so a big weather event that flattens crops or a flood, insurance companies need to know who has been affected as soon as possible so they can process payouts for the farmers who lost their crops. So what's key in terms of the form that information needs to take? We'll come back to these points, but the information needs to be on a plot-by-plot basis for each farm field, and we need to be able to cover a large area. Insurance companies in the PMFBY operate on districts at a time, so that could be millions, tens of millions of hectares. And so unless our system operates on that scale or near that scale, it's not going to be of use to insurance companies. Obviously, the timing of data is important and keeping the cost as low as possible. So let's take on the question of area coverage first. Obviously, the higher you fly, the larger your field of view with any given camera. But a few other factors play a big role in how much area you can cover, namely airspeed, flight endurance, and row overlap, as we've seen from some of the earlier presenters. If you're thinking about UAV operations and really maximizing your area, you end up being limited by UAV flight time. It's been mentioned a couple of times already today. So we have to plan for multiple flights with battery swaps in between. But how do we take advantage of UAV's primary advantage? Their size. In this case, we're going to make some assumptions, and we'll come back and revisit them later, but we're going to assume that we have multiple UAVs in the back of a van with a single operator. That operator drives to a location, launches all of the drones. Let's say they have 4 or 5 drones in the back of the van. The drones fly their surveys autonomously, then land. The operator downloads data, swaps out batteries, uploads new flight plans, puts everything back in the van, drives to the next location, and does it all again. In that scenario, how much area can we cover with drones? This is the result of a simple geometric simulation where each of the dashed lines shows one or more EBSQ, which is a fixed wing drone that's really designed for, aimed at the agriculture sector and is designed to cover the maximum area with a given battery. So you can see, based on AGL as the above ground level, so based on how high above the ground you're flying, 5 drones in the back of a truck with a single operator can actually cover quite a bit of area. Now, for comparison, this is the black line that you see is from a single Cessna 172, which is a small piloted aircraft. You'll see the curves in these lines really are based on come from the fact that the drone with its limited battery life has to go up, fly a survey, come back down, batteries get swapped, goes back up. And so that time going up and down to altitude ends up taking away time that you can fly in your survey. And so the higher you are, the higher that survey has to be, the more time the drone spends going up and coming back down for battery swaps. So it's clear that 5 drones in the back of a van can easily beat a Cessna airplane in terms of area coverage. But you all probably see the problem with this plot. here we're assuming that drones will fly their surveys at 2,000 feet in elevation, or 3,000 or 4,000 feet in elevation. Drone regulations, as it has come up multiple times already, are a big factor. First off, there are natural limitations. Cloud cover, particularly during the rainy season, is going to limit us to 2,000, maybe 4,000 feet above ground level. But bigger than that for drones, obviously regulatory limitations come into play. 120 meters on this plot is right here at these stars on the far left-hand corner of each of those colored lines. And so the 5 drones in the back of a van flying at 120 meters AGL is not going to get you much area coverage. You might be able to cover about 23,000 hectares in a day. The other limitation is that the scenario that I've described obviously isn't legal yet, let alone the flying height. The current regulations require you to have a single operator for every drone that's in the air. Now, there are places working on solving those problems, mostly not in India, unfortunately, but eventually they will happen. And I do believe that eventually drones will be the right answer in this particular situation. The technology is there. It's the regulations that need to catch up to it. So what does this mean for cost? So looking at the same 1 to 5 EBSQs flying at the allowed altitude, in this case the Cessna is flying at about 4,000 feet. We come out at a cost per hectare coverage. Now this assumes flying twice per week. So a cost per hectare for the season of about 50 cents, both for 5 EBSQs and for the Cessna flying at 4,000 feet. But the difference in area covered, now this is a log plot on the bottom, so the difference in area coverage is about 7x. So the piloted aircraft hectare per day, the 5 drones together can cover about 23,000 hectare per day. And so the key here is that most people assume that a piloted airplane is too expensive to even consider. But if you're covering 7 times the maximum that a drone setup can, or in this case, the airplane is covering 35 times the area than a single drone can, then the piloted airplane actually becomes cost competitive. So moving on to plot by plot, this other second requirement that we really need plot specific information in order to make this system work. It's clear from the previous slides that we really want to fly as high as we can to maximize area coverage. But how high is too high? Turns out that the answer is based on 2 factors, both the size of the pixel and how well we can locate it relative to the farm plots. How well can we actually register that plot in the area that we're looking at? So these are 2 extremes that we're looking at. On the left is an image from Sentinel-2, where you can, if you squint, you can barely make out, you can guess where some farm fields are in there. But it's a computer to do that automatically would be a pretty tall order. On the right is some imagery from a MicaSense Red Edge camera mounted on a drone flying at 400 feet AGL. It's very clear where the plots are. Here, obviously, they're highlighted, but it's a fairly trivial matter to determine which areas are fields and which areas are not. As I said, so we're looking for something somewhere in between. So how high can we fly and how large can we allow that pixel size to be and still be able to distinguish one plot from the next? But pixel size isn't the only issue. Because we're looking for plot-specific information, we also have to be able to say which point on the ground is represented by a particular pixel. For that, we have to be able to register that pixel accurately. Sentinel-2 data, for example, has 10-meter pixels, but can also be misregistered by as much as 10 meters. This means that we have to buffer our plot outlines by that amount in order to be certain that the pixels we think land in that plot actually do. On the left, if the green line is the outline of a plot, of a farm plot, and the black grid represents the pixels in our image, we see that 3 pixels land entirely inside the plot boundary. All the other pixels lie at least partially outside the plot. So we can't trust the reflectance that we get from those pixels. We have to discard them. In the middle, though, we realize that we don't actually know what the position of that pixel is within that grid very well. We're uncertain of its distance or of its location by a distance of sigma x. So we have to add this buffer. And that buffer pushes it over the edge of the crop, over the edge of the plot boundary. So that means we have to discard that pixel. So another way to look at it is that that buffer can be added to the inside of our plot boundary. And we see that 2 of the pixels that we thought were valid actually are not, because they could intersect the boundary of the plot based on how accurately we know its location. So that larger pixel location uncertainty leads to fewer valid pixels in each of our plots, which means we need to fly lower in order to get more pixels that we do know land inside a plot, which makes the whole process costlier and all of the surveys costlier. So the work that we've done image processing that allows both a reduced need for overlap in the surveys. We also improve the image registration, so we reduce that need for a buffer on the inside of our plots. And in the end, it allows higher flights. So what we do, we've outlined the plot out. We use, sorry, the way that we do that is by using high-resolution satellite imagery as a base map. And so once per season, we will take the satellite imagery at 0.8 meters or so, something that we have to purchase from a company like Digital Globe. And we'll outline the plots. And then each of the multispectral images gets registered to that base map as opposed to the other multispectral images. So we're not building a mosaic as most image processing or most remote sensing imagery ends up doing. Instead, we're trying to maintain that information, as much information as we can from each of those images, by overlaying and registering those multispectral images to the base map. And that also allows us to move away from the requirement for a 60 or 70 or 80% overlap between our flight rows. So, given the user needs that we've identified, what makes the most sense for the application of wide area crop monitoring of individual farm plots? For now, given the regulations, the best platform to use is a piloted aircraft, such as a Cessna 172. There, we're meeting the needs for the maximum area coverage, while also meeting the needs for plot-by-plot data resolution. We can take advantage of a higher survey altitude while keeping a small enough pixel size and keeping that pixel location accuracy. And so for now, for example, a MicaSense Red Edge flying at 4,000 feet, and this should actually be 1,200 meters AGL, sorry about that. We can cover about 170,000 hectare in a day with a pixel size of about 1 meter and pixel accuracy of about half of that. The other advantage of using a piloted aircraft is that sensor weight isn't an issue. And so one of the things we're exploring is adding a hyperspectral sensor, adding a thermal sensor. We're not worried, we're not concerned about the weight of the sensor on this particular platform, and it opens up the possibility of using either higher end or simply more sensors in order to get more data. I do believe that drones will have their day. The regulatory issues need to be taken care of, but the technology is there. As I said, both allowing drones to fly in general aviation airspace is a critical factor, and allowing swarm operations, allowing multiple drones to be flown by a single operator. It will happen, but for now, the manned airplane really maintains the advantage. So now the question comes as to what to do with the images once you've actually captured them. And here I'd like to describe one particular approach. And this is really, the first piece is really maximizing that reflectance data. So we talked a little bit about one of the downsides of flying higher is obviously you have a larger air column between your target, the plot, and your sensor. Luckily, aerosols in the atmosphere typically come into play from about 1 kilometer to 10 kilometers above ground level. And so if we stay on the bottom edge of that, then we're not that concerned about aerosols affecting our reflectance numbers. Comparing to satellite imagery, the goal accuracy of that bottom of the atmosphere reflectance is about 5% from Sentinel-2A. Compared to that, the reflectance factor error for the drone camera from a typical market sense is less than half of that. And so for the reflectance precision, we're in relatively good shape. So the difference that I talked about, one of the advantages that I talked of that system that I talked about where we're registering each multispectral image to the base map itself. Here we're trying to maintain as much information in the imagery through the data processing as possible. So most people think of the mosaic that comes out of a drone image as uniform. You can think of it as taking a single snapshot at the same time. But in reality, that mosaic is made up of images taken from different angles at slightly different times. And yes, they are very close. But the reality is that we're not sure if you look at an individual pixel in a drone mosaic. You can't necessarily tell which capture that came from. Or it may have come from, it may end up being an averaging of multiple captures. And that information is lost in the processing of that drone imagery. So that's what I'm trying to avoid. So we use what we call a layered data approach. So here we're taking each image from one particular time point. Our pixels are larger, but we know which pixels are inside of single plot. And we store that data from a single capture. And then we take the next capture, and it has its pixels that land within the field, and we store that data. And then the next capture gets layered on top of that. And so we may end up with as many pixels within that field, but those pixels are going to be overlapping spatially. But the key is that for each of those pixels, we know what that camera position was at the time that that picture was taken. And so for each pixel that we determine is valid within a field, we get that additional set of data of the sun position, which we already know at the time, and the camera position. And so we get additional data to put into machine learning or artificial intelligence algorithms. And we can also choose subsets of that data. For example, we can choose to only look at the pixels from the outside edge of each of our images. And there we know roughly at what oblique angle those pixels are taken, because our camera has a 42-degree field of view. And so we can we can choose to look at an angle if we want to, say, avoid extra soil reflection from between rows. If we know what direction the rows are going, we can choose to only the pixels that are looking at that field from an angle that would not see that soil. Or, for example, we can look at a comparison of the reflectance versus the viewing angle in order to get a better sense of crop height or row orientation for crop ID. So there are additional options for data processing and investigation that are enabled by keeping track of that information of which, for each image, which camera angle and which sun angle were in play at that time. So, putting this all together, what does this look like in actual implementation? I showed one picture earlier of a MicaSense camera mounted on a Cessna 172. This is the same camera actually mounted on under the wing of a Piper Cherokee, a different aircraft. This one happens to be in Uganda. So we currently have a couple of pilot projects either underway or in planning. One in Karnataka working with the Deshpande Foundation, one in Jinja, Uganda, working with One Acre Fund, and we're doing some work here in the U.S. Because I happen to be here for the moment because of COVID-19. Now we're doing all of this under the auspices of Viridis RS, which is the startup company that I founded with our CEO, Hee-Jae Cho, after I finished my PhD. And we're working with our co-director, Aditya Bhatt, in Bangalore. And so the work that we're doing here is really trying to commercialize it, trying to take this, this technology, tweak it as we learn more from insurance companies and make it better match what they need, and eventually to turn it into a sustainable business, because that's really how this can grow. And so I want to bring this back to the original reason why we're doing this work, and that's to serve smallholder farmers. There's so often a push to get the most pixels or the smallest ground sampling distance out of your technology. But if we look at the actual needs of our customers and provide only what they need and not more, then we have a much better chance of creating something useful, something valuable, and something lasting. And so here we're really trying to answer this question of how can we create an individual insurance product for smallholder farmers to help them manage their risks, to help them grow, and to help the insurance companies better serve them. Thank you very much. I will, let's see, I can look at I stop sharing. I'd be happy to look at the questions and comments. Oh, I'm afraid I saw this too late. Apparently my voice pitch is too low. Were people able to hear me and understand me?
Yeah.
Good.
Thank you, Dr. Mark, for nicely explaining how you do all these crop loss and giving a background of insurance and how potentially we can use this technology. And I think the kind of platform what you have, just I have a query if nobody is asking, how about the regulations for this kind of drones to fly in country like here in the US? You have a huge fixture, it's kind of a helicopter. So it seems so. How do you manage to do that, and what is that?
So there are lots of regulations around piloted aircraft as well. That's true. We currently have an application in with the DGCA. They do have a process for getting approval to mount a camera on an airplane. it takes some time, but we expect that to come through with the support of the state government for that, in this case, the Karnataka state government, for that project. It's a process that we've gone through multiple iterations and been frustrated by it a couple of times, but we expect the regulation side of things to be much smoother going forward once we set precedent for that. In the US, the regulations are actually for putting a camera on an airplane, they're actually quite minimal. There are safety considerations that are handled by the Federal Aviation Administration, but ultimately it's the responsibility of the pilot in charge. And so if, as long as you can find a pilot who's willing to let you mount your camera on their airplane, there's nobody to say otherwise. Which does make it easier for us to do experiments here, but unfortunately the field sizes in the US are too large to really get comparable data. So in order to really test our system that's intended for smallholder farmers, we need to fly somewhere with smallholder farms. And so for that reason, that's part of why we went to Uganda, because the regulations there are a little bit easier. But they do have smallholder farms. And so we're trying different channels. The final answer in India is still yet to be seen, but we've gotten good feedback from our aviation partner, and we expect to be able to fly hopefully within the next month or two.
Great. Some people are asking about how do you assess loss due to weed, because it's a low flying imaging, so you should be able to discriminate weeds from the crops. And is it possible, or is it some success story is done?
The assessment for weeds we've not done, and because we're trying to fly as high as we can and maximize that area coverage, our pixel sizes are actually quite large. So we end up flying with about a 1 meter pixel. And so we're not able to pull out to distinguish weeds specifically because our pixel sizes simply aren't small enough. What we can measure is crop stress, and we're utilizing some of your research, Ravi, in choosing which wave bands we're detecting and which vegetation indices we're detecting in order to measure the crop properties using that larger pixel. So as you know, one of the issues with hyperspectral sensing is that you end up having a large pixel and trying to distinguish information within that pixel is a real challenge. So we're taking advantage of some of that research because our pixels are too large to distinguish things from one space to the next. Our goal is really to get an assessment of each individual plot on its own.
Yeah. So I think some of the basic studies we have done in IRE itself using spectrometric data to discriminate weeds from weeds, and also density of weeds, which is going to affect the economic yield of the crop. So some of the basic studies we have done, but again, the challenge remains is mixed pixel in a pixel having weeds and wheat. That kind of challenge. Of course, spectral unmixing, all those algos can be used to address some of them.
And all of that, it's really translating that research into a practical system that can collect data cost effectively.
Yeah. Mark, there are a couple of questions they focus to. You collect so huge data. Is that you are using some high-end computing system, commercial softwares? Because they're very expensive to invest on doing the drone remote sensing, as people say. So how to do that? How you do such a huge data to analyze and do a quick delivery? Do you have any kind of estimate you ask?
So there are a couple pieces to that. We do end up with fairly large data sets. The processing that we're doing is all in the cloud at this point. It's on and Amazon Web Services. And as we need to, we can spin up more resources. The other piece about that technique that I mentioned of taking each multispectral image and registering it to the satellite base map is that it's not quite as resource intensive as building a mosaic. Because in a mosaic, you need to take one image and match it to multiple other images at the same time. And so you end up, the resource needs for that are a little bit higher. In our case, I don't have any direct comparisons for time, but we don't need quite the level of computing resources that building a really large mosaic would require. So it's a combination of the technique there and really just taking advantage of cloud computing and the computing power that's available there.
So do you have any effort to see the loss assessment because of what? Either because of biotic or abiotic stresses or what? Do you have any kinds of case studies using the kind of sensors you have developed, or is a future line of action you have?
So I did some sensor development during my PhD work, but it was really a basic sort of adjustable multispectral sensor. And so there are commercial sensors that we can buy off the shelf right now that are much more robust and can handle the rigors of being mounted on a piloted aircraft. And so I've shifted away from sensor development itself. The question of what we can actually measure really depends upon the crop. For the Karnataka project, we're really focused on cotton at the moment. Some of that is driven by where can we get the ground truth data that we need to really validate the aerial imagery. And so we have a partner with the Deshpande Foundation that has close contacts with and relationships with a number of cotton farmers in the area. And so we can leverage their network for getting ground truth data. The big question for cotton is obviously pink bollworm. That's a really challenging thing to measure from a remote sensing platform. There's some research out there suggesting that it's possible. We haven't validated it yet for ourselves yet. So at this point for cotton, we're really looking at crop stress. We have a thermal camera that's able to do a little bit of water stress measurement and mapping of not quite groundwater, but we're starting to look at soil moisture in that case as well. And so what you can measure obviously is going to depend upon what crop you're looking at specifically. In Uganda, we're looking at maize, and there's quite a bit more research out there in terms of what you can measure with maize. I don't off the top of my head have the top types of stresses that they're concerned with in Uganda. That project won't happen until March. But we'll be looking, sorry, I'll try to hold my microphone up a little bit closer. But we'll be looking through the research to decide which vegetation indices we really need to look at for maize specifically.
Okay. And I think one question is whether a smartphone can be used for crop loss assessment.
That comes down to the question. Well, that's a better question for you, Ravi. Actually,
yeah.
If a smartphone were to come out that could provide, the question really becomes, what can you do with a silicon sensor? If the smartphone is inherently, you're not going to get a thermal camera in a smartphone, and so let's say there was a farmer's smartphone that was developed that could give narrowband multispectral images. Do you think that would be useful?
That's still in a research mode, but what I would like to inform here is to the House is, in the ministry, they have developed some apps to collect the crop information and get down to the server so that you can get a detailed crop information related to not only crop and also crop cutting experiment details, so that there they can get the assessment. But the question I think more of is, if at all the sensor what is integrated in a mobile, that's RGB, if it is possible to know the loss, I think to some extent yes, we are yet to come out with some solutions like this. As I told at the beginning, with the RGB camera you can do some kind of a IMS leaf area index and also greenness of the leaf assessment. And also you know the crop growth from that perspective, but quantifiable term you need to derive and go for modeling to assess that.
I think one of the real challenges of using a mobile, and this may be solvable. Anytime you're assessing that yield, it really needs to be turned into a yield per area. And so, in my experience, many farmers don't actually know how much area they have in each plot to a very precise number. They might know to within half of an acre. But in reality, to get an accurate yield number, you need to know pretty closely, precisely what the area of that plot actually is. You know, and there was a question that came up about correlating yield loss percentage to threshold yield. That's really going to come down to what the area is. So an analysis from a camera image might be able to give you a weight per area if you know the area that picture is actually taking a picture of. And that threshold yield is going to be specified as a weight of crop per area. And so getting that area information is just as important as getting accurate measurement of the crop yield.
So there is a question, I think there is expectations from the speakers saying if a spatial data analysis can be applied to drone data analysis to address some agri applications. I think it's a very common question. I think in drone you get a spatial data, pixel-wise data. So whatever applications you look at, whatever the information you are going to retrieve, that is in the spatial scale only. And not only spatial, dynamic scale, spatio-temporal scale, you are going to get all those data. So of course, all those spatial modeling is going to be used, applicable to know where what kind of crop condition is. Accordingly, one can go for management. And there is one question, I was not very clear about that. And don't you think more important for India is to consolidate farmers into measurable units than reduce measurements to lower level?
That's a big question for agriculture in general. I do think that Indian farmers will not really be able to take advantage of mechanization until the average plot size increases drastically. There's a reality, both given labor shortages within the agriculture sector and the cost of cultivation. I think I do agree that at some point the land needs to be consolidated, whether that's through a cooperative model or through opening up of land rights to allow individuals or companies to consolidate that land. But in order to get to more efficient farming, both energy efficient and cost efficient, eventually the plots will need to be combined. In the meantime, the question is, how do we get to that point?
Yeah.
And there are still lots and lots of farmers in India who are getting by on small plots. And I think that consolidation will eventually happen on its own as more and more people, as further generations either move to the city or decide that they don't want to farm anymore, or get interested in the technology side and see that requirement of consolidation before they can really take advantage of the benefits of farm mechanization. And hopefully by that point, we will have figured out how to cover even more area at once and take advantage of remote sensing even more so.
Yeah.
I don't think it's a question of one or the other, but I do agree that consolidation really needs to happen.
Mike, I have last questions for you is yeah, how we can correlate yield loss percentage to threshold yield, and then finally to the crop insurance from the drone data.
Right. So that again comes back to, first off, having the crop area. So the threshold yield is under the PMFBY is really determined by historical data. And so in order to have a purely remote sensing based solution, you need to have years of remote sensing data. For the time being, we can use the historical data from the village that already exists from the Gram Panchayat, which is average data. And then correlating the loss percentage. So if you have the expected yield, the yield models that we have, we're still testing how precise they are, how accurate they are relative to a ground truth. But if you have a precise enough yield model based on the remote sensing data and weather data and the other inputs that you can put into that yield model, then you end up with a measured or an estimated yield at the end of the season. Comparing that to the expected yield, you get your loss percentage. And then really the comparison to that threshold yield, that's going to end up determining whether or not you get an insurance payout. And so all of that data needs to end up at the insurance company. And one of the struggles that insurance companies have is being able to trust the information that they get. Right now, as the system exists, the insurance company receives information from the farmer when the farmer signs up for a policy, or from their bank, or from the state government. There are enough examples out there of farmers choosing to sign up for insurance for a more expensive crop and then going and planting a cheaper crop. That's one way that farmers game that system. And what that ends up doing is it increases the premium cost for everybody else, because the insurance company has to take that into account. And so the insurance company is looking for independently verifiable data. And that's something that Viridis is offering in terms of this data collection, by having a transparent process by which we collect the aerial imagery under a known procedure. We process that imagery independent of the government, independent of the farmer, without influence from the insurance company. Then the insurance company knows that they can trust that data. And having that third-party verification is something that's really critical for the insurance company to integrate that into their operations. I mentioned a little bit about the way that insurance works in industrialized areas like the US. When that insurance company representative goes out to the farm and visits the farm at the end of a season, it's not just the farmer saying, this is what happened, and I didn't have a good yield. The farmer has data from their tractor that's already collecting information about their crop. The farmer has already taken their crop to sell it to the market, to the grain elevator. And they have receipts from that operation that they can show to the insurance company representative. And so those are examples of that third-party information that the insurance company has. And most likely the insurance company has already purchased satellite information, or maybe airplane-based remote sensing information. So the insurance company has that third-party information in order to verify what the farmer is saying. And that's really one of the things that's missing in the current crop insurance system in India, is that third-party verifiable information, so that the insurance company has trust in what they're hearing, so that they can make a financial decision, a policy or claims decision based on that information. And so in this case, we're providing that yield estimate at the end of the season of what's actually come in, and we can do that comparison to what was expected and to what the historical threshold yield is. And so the insurance company, with all those pieces of information, can then make its decision on claims, and hopefully do that quicker than it can right now. That's really required on state representatives to go out and conduct crop sampling experiments. Let's see, are there other?
Mark, I think you got a lot of appreciations for a wonderful informative talk on such a burning topic. And thank you so much, especially staying awake.
Thank you very much. I'm happy to be here. Very happy to be able to contribute and to be part of the conversation.
To see you, and we'll be in touch. And again, I would like to tell because I know you are going to be at New Zealand, but you are online. So affiliation address is given New Zealand. So we thought of sending some token of appreciation to your residence address online.
Thank you very much.
So again, this is all effort and appreciation from Chairman of Indian Institute of Agrophysics, Dr. Chaudhary, DDJ-NRM, and also Dr. Pramila Krishnan, who is heading Agriculture Physics. So on all their behalf, I thank you for a wonderful lecture and sparing whole night till midday with us.
Thank you for having me.
Thank you so much, Mark. See you.
Bye.
Thank you, Mark, for your kind presence. Thank you very much. It was a wonderful lecture. Thank you.